All right, last time we met, we just introduced the law of conservation of mass. Law of conservation of mass. And basically what that says is, like making sandwiches. Have you ever had a peanut butter and banana sandwich?
No. Yeah.
You have? Well, you start with bread, you put bananas on, and you put peanut butter on. And however much bread you start with and however many bananas and peanut butter you start with, the mass you start with equals the mass in the end, right? And we also said, for example, a chemical reaction like A plus B going to C plus D, right? If I know I have 1 gram of A, 3 grams of B, and in the end I produce 2 grams of D, how many grams of C am I going to produce?
What's the total?
The total over here is 4 grams.
Oh, 2 grams.
That's right. It has to be 2 grams of C. So the mass of the reactants will always equal the mass of the products. Very good. So this slide here shows a problem where we say magnesium, that's Mg, burns in oxygen to form magnesium oxide, that's MgO. If 16.88 grams of magnesium are consumed and 28 grams of magnesium oxide are produced, what mass of oxygen was consumed? How are we going to find that out? How are we going to solve that problem?
28 grams minus 16.88 grams.
Good, because magnesium is the 16.88 grams, and the magnesium oxide that's formed is the 28 grams. So this plus however much oxygen has to equal 28 grams. So, very good. I'll get my calculator here, and I'll type in 28 minus 16.88, and my answer should be, what's it say there, 11.12. So I get 11.12 grams of oxygen. Very good. And that's because the law of conservation of mass. Whatever you start with, the mass of it ends up being the mass of the products. Now remember, we also said that one example was if I had 2 hydrogen gases and I combined it with 1 oxygen gas, I would make 2 water molecules. All right, I'm going to make this 1 look more like a 1. And I said if I had 1 gram of hydrogen and 8 grams of oxygen, it would form 9 grams of water. If you look at the equation and you don't understand what the equation is saying, you might be confused into thinking, wait a second, this is saying 2 grams of H2 and 1 gram of oxygen yields 2 grams of water. Why is it somebody else is saying 1, 8, and 9? And the answer is because this 2 and this 1 and this 2 here, those are not mass, right? This is saying 2 atoms of hydrogen, 1 atom of oxygen, 1 molecule of oxygen gas, 2 molecules of water, right? It's not saying 2 grams of this, 1 gram of this, and 2 grams of that. Okay? So we'll have to keep that in mind. Another thing that we can do with the law of conservation of matter, another chemical law that we're going to introduce is what's called the law of definite proportions. The law of definite proportions. And that means that if I have a reaction that combines hydrogen gas with oxygen gas to form water, for example, if this is my chemical reaction, and every time I combine hydrogen gas with oxygen gas, in a certain way, it forms water, then these are the proportions, kind of the ratio of hydrogen gas to oxygen gas, 2 to 1, to get 2 of these, that I need to combine them. If I put in 3 hydrogen gases and combine it with 1 oxygen gas, I'm not going to be able to get more water. I'm still only going to get the same amount of water. I'm just going to have a leftover hydrogen gas, because this is the proportions in which the reaction occurs. Let's do a different example. If I have 2 A's combining with 1 B to form A, 2, B, and if I then, using this same reaction, put in 3 A's with a B, I'm not going to get something else. I'm going to get the same products, A to B. I'm just going to have what left over? An A. That's right. I'm going to have an A left over. And this is the law of definite proportions. Another way to think about the law of definite proportions is if I have 2 piles of a chemical. Let's say this is sodium chloride. I have 1 pile there, and I have another pile here. This is a small pile, and this is a large pile. Okay? If I know that this pile here has 23 grams of sodium and 35 grams of chlorine in this pile, and this pile over here has 11.5 grams of sodium, I can know how many grams of chlorine are in this pile over here because they're both made of the same material. And so the ratio between the grams of sodium to the grams of chlorine will be the same. So if I know that the ratio of 23, or the grams of sodium to grams of chlorine is 23 for every 35, 23 grams of sodium for every 35 grams of chlorine, it has to be equal to this other pile over here. This is supposed to be the bigger pile. Let's make this the smaller pile. Sorry, this is a smaller pile now. It has to be equal to 11.5 grams of sodium over X grams of chlorine. So I can find out how many grams of chlorine will be in this pile by solving this problem. And to solve this problem, you multiply these two together. So that's 23 times X, some unknown number, and that equals, multiplying those two together, the product of those two, 11.5 times 35. Okay? So I can put that into my calculator. What's that? Do you have a calculator? You want to do it? What'd you get?
Well, first I did 35 times 11.5
Uh-huh.
equals 402.5.
Okay.
And then divided it by 23, and that equals 17.5.
Very good. That's right. That's how many grams of chlorine are going to be in this smaller sample. Very good. And the reason we could do that is because we knew that both of these masses of material were the same. Therefore, the ratio of the grams of sodium to the grams of chlorine have to be the same if we know that the law of definite proportions is real. Okay, now here's another problem for us to work on. Here's another problem. A sample of magnesium oxide has 16.89 grams of magnesium and 11 grams of oxygen. What mass of oxygen would there be in a smaller sample that contains only 2 grams of magnesium? How would we set this one up?
2 over x.
Okay, good. 2. And that's grams of what?
Magnesium.
Magnesium over x grams of what? Oxygen. Very good. And that's equal to what?
16.89 magnesium.
Yep, grams of magnesium.
11.11 grams of oxygen.
Very good. Excellent. So, can you identify how many grams of oxygen then are in the smaller sample?
1 second. I'll use my calculator.
Sure. Okay, so how did you do it? What did you do now? In your calculator?
I did 11.11
Uh-huh.
times 2
Uh-huh.
equals 22.22,
Okay.
and then divided that by 16.89.
Okay. And what?
And the answer is 1.31.
1.31 grams of oxygen?
Yeah.
Okay, very good. That's right. Oh, was it 1.315 grams? It's okay. 1.31 grams. Very good. Excellent. Way to go. So, again, we could do that problem because of the law of definite proportions. Good. Excellent job. Now, let me talk to you about what we call Dalton's atomic theory. Dalton, a long time ago, a gentleman named Dalton, said that all matter was made of atoms. He said that atoms could rearrange themselves and move around. However, they can't break themselves. The atoms can't be destroyed. So in chemistry, we watch how atoms can move from one atom to another and form new bonds, break apart and form new bonds. But the atoms themselves never break and destroy and become something else in chemistry. All right? So, Another law, so that's called the atomic theory, is that atoms themselves never change into other atoms. Another law is called the law of multiple proportions. And what this basically says is that sometimes you can react two things together. So here I'm reacting sulfur with oxygens. And if I react it one way, I get sulfur dioxide, sulfur with two oxygens. But if I react sulfur with oxygens a different way, I can end up getting sulfur trioxide. So that is called the law of multiple proportions. So we have the law of definite proportions, where if you react two chemicals the same way, you'll always get the same product. But we have the law of multiple proportions, which says that if you react two chemicals different ways, then you might get different products. Okay, now we're going to look deeper at chemical equations. We've already kind of used chemical equations a lot as in examples, and we're going to look deeper at these equations. Here's an example of an equation here. It's a full equation, right? We have two HCl's reacting with one. See, there's no coefficient there, but when there's no coefficient, we always remember that it's actually a what? It's a 1. That's right. It's a 1. So we have two HCl's reacting with one CaCO3, calcium carbonate, yields one CaCl2, calcium chloride, and one water and one carbon dioxide. We also see these little letters down here, which we've talked about before. What does that S mean? Do you remember? It's not liquid and it's not gas.
Oh, solid.
Solid. And what does the L stand for? Liquid. And G stands for?
Gas.
Gas. Very good. Now we're going to introduce a new one. AQ. AQ stands for this word right here, aqueous. Aqueous. And aqueous means that the substance is dissolved in water. So it's not liquid, it's just dissolved in water. Does that make sense? Dissolved in water?
Yeah.
Okay. Very good. So, in this chemical equation, we need two HCl's to combine with one calcium carbonate, because if you don't have two, then you'll have extra calcium carbonate that won't react. And so the stoichiometry, that's a big word. That means we're only looking at the numbers in front of the reactants and products. And the stoichiometry here is two of these for every one of those, and it produces 1, 1, 1 of each of these, right? And for an equation to be balanced, because we're not making or destroying atoms, we have the same kind of atoms on the left side as we have on the right side. We're not destroying or creating atoms. Therefore, the equations have to be balanced. The number of H's on the left has to be the same as the number of H's on the right. So now, like we were doing before, where we would identify the number of elements in given compounds, now we need to identify the number of elements on the left side of the equation. So what kinds of elements do we have on the left side of this equation? We have hydrogens, right? We have chlorines, So I'm going to start making our list here. Hydrogens, chlorines. What else do we have? Ca. Do you know what Ca is? Calcium. Calcium. The C all by itself, that's what? That's carbon. All by itself is C is carbon. And then we have O. What is O? Oxygen. Very good. And then the reaction occurs. Now, do we have the same elements on the right side of the equation? We should, right?
Yeah.
Do we?
Yeah.
We have H, we have chlorine, we have hydrogen, chlorine, calcium, carbon, and oxygen.
Yeah.
Now let's see that the numbers of each of them are the same. How many hydrogens do we have on the left side of the equation?
2.
2. That's right, because this 2 in front means we have 2 of these HCl's. Very good. How many chlorines do we have on the left side of the equation?
2.
2. Very good. How about calciums?
4.
No, on the left side of the equation, we just have in this compound here, right? And this is 1 Ca, 1 C, and 3 oxygens, right?
Yeah.
So there's just 1, right? Of the Ca, can you? What's that?
Doesn't the 2 in the front hit all of them make them 2 more?
Oh, good point. Good point. But no, because of the plus sign here, it's saying that this thing here is being added to just 1 of these. All right, so that 2 only goes for this chemical right here. Very good point, though. So 1, very good. How about carbons?
2, 1.
1, good. Oxygens?
3.
3. Very good. Now let's look on the right side of the equation and see if we have the same number of elements on this side. How many hydrogens? 2. Very good. Chlorines?
2.
Yeah, 2 chlorines. How about calcium?
1.
1 calcium. Good. How about carbons?
1.
Yeah, 1 carbon. And how about oxygens?
3.
Yeah, 1 here, right? And then 2 over here. So we've counted all the atoms on the left side of the equation, the different elements, and counted all the elements on the right side. And because they're the same, we can say this equation is balanced. Okay, very good.
Wait,
Yeah,
why does never mind, that's an L, not a 1.
okay, good. Good question. All right, so here it is. Here's an opportunity for us to balance our own equation. Let's look and see what kind of elements are on the left side of the equation here. What kind of elements do we have?
We have carbon,
Carbon,
hydrogen,
hydrogen,
and oxygen.
okay, very good. Oxygen. Now hopefully those are the same things we have on the right side of the equation, is it?
Yes.
Nothing new? Carbon, hydrogen, and oxygen? Okay, very good. Now, how many carbons do we have on the left side?
Carbon's
8. Very good. How about the right side?
1.
Just 1. That's right. How about hydrogens on the left?
18.
18. How about on the right?
2,
2. Okay. How about on the left? Oxygens.
3,
On the left side or the right side?
2,
2. Okay, good.
3.
3. Is this equation balanced?
No.
It's not balanced. All right, so let's look at the carbons to start off with. How many more carbons do we need on the right side?
7.
We need to have a total of 8, right? So we need 7 more, right?
Yeah.
So I'm going to write the equation down here for us. C8H18 plus O2 yielding carbon dioxide and water. If I put an 8 right here, that will change us to have how many carbons now?
8.
It'll have 8 carbons, won't it? It'll also change the number of oxygens. So now I'm going to make another row here because I made a change. So instead of 1, now I have how many instead?
8.
8. How many hydrogens do I have?
2.
Yeah, still just 2. But how many oxygens now?
17.
Very good, 17. All right, so I made the carbons the same, but the hydrogens and the oxygens are still not the same. So what can I do? What's that?
Never mind.
Okay, so what can I do now to get more hydrogens on the right side?
Well, you could have put the 8 right next to the carbon, but under it, like instead of in front of it, you could have put it to the right side of it, but smaller.
Okay, well that is a lesson we have to learn as well. Let's talk about that. Because something happens if I try to do that. If I take this chemical, carbon dioxide, and put an 8 in front of it, it now means I have 8 of these, right? Does that make sense? When I put an 8 in front, it means I have 8 of those. But if I go like this, C8O2, this chemical here is not the same chemical. This is something else. 8 carbons and 2 oxygens. I have 1 of these C8O2s, but that's not the same as having 8 of these CO2s. So I can't balance an equation by changing the compound or changing these numbers down here. I have to only change the coefficient in front. Because if I change the compound like this, H2O, and maybe I want another oxygen, so I go H2O2, those are different chemicals now. Completely different chemicals. All right? So I can't do that. I can only change it by putting a number in front of it or changing the coefficient. So if I want to get more hydrogens and I only can change the coefficient, what number can I put there to get more hydrogens? I need to have 18 and I only have 2 right now.
9.
9, very good. I put a 9 there and now that changes the number of hydrogens. How many hydrogens does that make me have now? 18. Very good. I still have 8 carbons. That didn't change, right? Did I change the number of carbons by putting a 9 there?
No.
Okay, now how many oxygens do I have on the right side? I had 17. Maybe we should start over counting. How many do I have? 8 times 2 here is 16 plus 9. 25 oxygens. Okay, so now look, I have Carbons, the same number. Hydrogens, the same number. Only oxygens need to be corrected now, right? And I need more oxygen on the left, don't I? So what number can I put in front of that one?
You'll be one off if you do it.
Yeah, I will, won't I? I have to put like 12.5, right?
Oh, yeah.
But you can't do that. You have to put whole numbers. You can't put half numbers like that. But what I can do, once I realize that 12.5 would work, 12.5 would make this 25, and I'd still have 18 here and 8 here, right? So these numbers are now the same, but I don't like to have half numbers like that. And so what I can do is I can multiply all the numbers by 2, and then it'll make that half number go away. What's 12.5 times 2? Do you know? What's 12.5 times 2?
25.
That's right. So if I said 25 oxygen gases, and if I want to multiply this one by 2, it would be 2 C8H18s. And then what would this one be? 16 carbon dioxides and 18 waters. Very good. So what we have there is a perfectly balanced equation. It's not 8, 18, and 25. It's 16, 38, and... Oh, no, not 38, 36. 16, 36, and 50. 16, 36, and 50. Okay. Did you see how we did that?
Yeah.
We changed the coefficients. That looks hard. That was hard, huh?
Yeah.
But that's all right. We started and we understood it. And next time we'll get better and better at it, and we'll practice as we go. Okay?
Okay.
Very good. Good job today. I'll see you next time.
Bye.
Bye.